All right, so number one, we're not going to need this first statement here. We're just going to concern ourselves with water being removed from the tank. Okay, and by the way, you guys have this worksheet 5, but I printed out solution keys if you want to grab one. If you wanted to look ahead. All right, so water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing. So differentiable, that just means that the rate is not going to all of a sudden not exist. It's going to be a smooth, continuous. R of T is going to exist for every point between 0 and 8. Selected values of R T are shown. At time t equals 0, there are 50,000 liters of water in the tank. Okay, so let's just talk about what's happening in this table. So at 0 hour, we have 1,300 liters per hour that is being removed from the tank, and then it continues to drop. Okay, so the rate decreases over this 8-hour period, but continually decreases. Okay, so number one, part A, estimate R prime of 2. Interpret the meaning of the value and indicate units of measure. So derivative, but it says estimation. So the way we estimate derivative is using slope. So we pick the closest points and we find the rate of change between 1 and 3. Okay, so change in rate over the change in time. And use your calculator. Units of measure, negative 120 liters per hour squared. So it makes sense, right? We're looking at this here. We're seeing, okay, the R of T is decreasing, right? And so that's represented here, right? That negative, we can see it from the table that is decreasing. And this is giving us a more specific detail that the rate is decreasing by 120 liters per hour. So we want to interpret the meaning. Anything that is at that second derivative level with that hour per that units per time squared, we always want to be able to represent it with indicating words like the rate is decreasing or rate is increasing. We don't want to say rate of a rate, okay? And also we don't want to use the word acceleration. It doesn't fit the context of this problem. Okay, so the rate that water is removed from the tank is decreasing by approximately 120 liters per hour at t equals 2. So I want to be able to looking for these words there to earn full credit. Okay, part B, estimate the depth integral from 0 to 8 R of t dt using 2 trapezoids. Trapezoids, we have 2 options. You can either go through the formula, which you can memorize and use, or you can do left rectangle approximation and then right rectangle approximation and add those 2 together and find the average, divide by 2. So if you don't want to memorize this formula, you can just rely on left and right rectangles and averaging them out. Okay, so just like how anytime we're dealing with a rate, our units will change. Same thing, if we're dealing with a definite integral, our units will also be changing as well. And look at what's happening here, right? You see R of t times dt. These are 2 units, that should remind you of multiplication, right? R of t times dt. And that's essentially what we're doing here. We're multiplying these units together. So after we go through our antiderivative process, we're no longer going to be sitting at liters per hour. It's just going to be liters, because liters per hour times hours would just be liters. Okay. So we go through two trapezoids from 0 to 8. So we can go ahead and identify our subintervals there. So from 0 to 3, and then from 3 to 8. Right? Subtract the t-values to get your width. And with trapezoids, we're only using the endpoints. Okay. Okay, so make sure that you're only using the y values that the bracket is coming down on. So we only use 1340 and 950, and then 950 and 700 for the second trapezoid. Okay, so we add those values together, we get 7560. So I want to kind of visualize this, what's happening, right? As water is being pumped or removed from the tank, there's different rates at which water is coming out, but ultimately at the end, what we can count on is we have some amount of water total that's been removed, right? So we don't want to be staying at rates anymore, because we've accumulated all that water over this time period, and eventually we're going to get something that's going to indicate the amount of water. So no longer liters per hour, is going to be in terms of liters. So over the 8-hour period, approximately 75-60 liters of water has been removed from this tank. All right, part C, approximate the average rate of water removed from the tank on the interval from 0 to 8. So average rate, that should remind us of average value theorem. So we set up average value theorem. And I forgot to indicate using the approximation from part B. So we're taking that value, it's still an approximation. So we can put that 7560 in for that depth interval. And then your A's and B's are 0 and 8. And then our units of measure is back to liters per hour, because depth integral is in terms of liters, but then you're dividing by time. So liters divided by time, you're going to be down back to a rate, liters per hour. Right, and then this number should visually make sense as well, right? If we're talking about an average rate, it should be consistent with what we see here, right? It should be a number that is between the highest and lowest values. So we want an average. Average means it's got to be lower than 1340 and higher than 700. And we do see something that makes sense. Yeah, that's fine, because it's already been indicated here. I just rephrased everything here, so that's fine.
say problem A was estimate R2 instead of like R prime of 2. Would like, or it was like interpret the meaning, and it wasn't like on that level, would be liters per hour, or just liters per hour.
Well, hold on, ask your question again.
Like if it was R2 instead of R prime of 2, would it be liters per hour or liters per hour?
Oh, if it's R of 2, then it'll just be 1190 or I don't think I would ask you R of 2 because then it's a guessing game. We don't know exactly. I mean, it's going to be between 1190 and 950, but you have no way of knowing. Yeah, so I wouldn't ask you that. Yeah. I would ask you R of 2 if I had a function where you can plug in.
Okay.
Fine, but table of values, it's either going to be slope or area, pretty much. Yeah. All right, everybody good? First page. All right, number 2, I'm making some adjustments here. I then found these things to add after I printed it out. So if you guys can do some changes here, interval is from 0 to 8 instead of from 0 to 6. So let me highlight that change. And then I added some additional instructions. Part B, justify your answer. Part C, indicate units. Part D, indicate units. All right, so using our calculator, we want to type into our y equals. Alpha trace, sorry, alpha y equals will get you that fractional setup.
I'll set the calculator here.
Oh, that's not yours.
Neither of them. Because I have programs in my calculator for ACT.
Yesterday I had Eric.
That just heard that one, but this is Sage's.
This is not yours. Okay, but what is it? Eric Schmidt. I also have the calculator. He must take me one. Okay.
I'll just, I know.
Okay. Thanks. Okay, I'm gonna adjust my window from, well, I'll do Zoom 6 here. Pretty good here. I can adjust my window or I can do a box around this region. I'm just gonna go to window and make it go from, I guess from -1 to, you don't have to, I just wanna, I don't wanna have to see all of that on the left side if I don't have to, so just makes it a little bit easier to trace. But yeah, you can always adjust your window with how far left and how far right you want your graph to go, and then how far down and how far up you want your graph to go. Or you can do zoom box and draw a box around the region that you want to zoom in on. All right, create a velocity and acceleration sine line. So looking for x-intercepts here. So second trace, select 0. I'm going to pick a point to the left of my x-intercept, hit enter. Pick a point to the right of my x-intercept, hit enter. Hit enter a third time. I get 3.5. If you get something like this, that y equals e to the negative 13 or something like that, that just means that's basically 0. That's basically y value of 0. So okay, I'm going to continue to look for another x-intercept here. All right, so I want to identify the signs of each of the intervals here. Above the x-axis, positive velocity, and then between 3.5 and 7, below the x-axis, negative velocity, and then from 7 to 8, positive.
I got 0 at 5.25.
Hmm?
I got my 0 at 5.25.
Oh, he did. But I messed up here. 2.5.
Oh, you know what I did?
Yeah.
It's cosine, so sine.
Yeah, sine.
Sorry.
Right, everybody good? Velocity sign line? Okay, so acceleration sign line, basically now we're picking off the peaks and valleys, the relative max, relative mins. So I see a relative max. So I'm going to do second trace. I'm going to select my maximum feature and under second trace. So I'm going to pick a point to the left of my of my max. And then I'll scroll over to a point on the other side of my relative max, hit enter. Hit enter a third time when they ask you for guess question mark. And I got 2.26. I see a relative minimum. So second trace, let's select the minimum feature. And now I'm just choosing points to the left and to the right of my relative minimum. .47. Okay, acceleration is the slope of velocity. So let's look at the slope here between 0 and 2.2. Positive slope, that means positive acceleration. 2.6 to 5.4, negative slope, that means negative acceleration. 5.4 to 8, positive slope. Find the times when the particle changes direction. We see two places where velocity is 0, but the change in signs also gives us that indication that there's a change in direction there as well. So our justification for there being a change in direction is the fact that B of t changes signs, and we see that demonstrated here on our sign line.
Say it was like positive after 3.5 because it like bumped the graph. Would it still change right? Like most of the x-intercept or no?
You mean it bounces off the? There will be no change. That just means that the object is going to stop for a brief moment, but then continue in the same direction that it was heading. Yeah. All right, part C, find the velocity of the object at t equals 2. So we're just no derivative here. We have the velocity function, so we're just doing a direct substitution, replacing 2 in for v of t. You can do it manually, or you can you just do a shortcut there, alpha y or alpha trace will allow you to reach that shortcut. And then do parentheses 2. Units of measure, meters per second. Part D, find the acceleration. Acceleration, we know, is the derivative of velocity, so we can involve math 8 and derive. Units of measure, meters per second squared. Sage, I got extra keys here if you want, if you need it. All right, next up is the particle speed increasing or decreasing from t equals 4 to t equals 5. So we know this is going to involve comparing our signs between velocity and acceleration. So we look at between 4 and 5. I lined up my velocity and acceleration sign lines, and my signs are both negative. And because they have the same signs, my speed will be increasing. And make sure that that you're also naming V of t and A of t as you are writing out your justification. Part F is the speed increase decreasing at t equals 2. You can just rely on this, or you can look at here, the same signs are still the same here, but they're both positive. Part G, find the total displacement. Displacement is just a definite integral, no absolute value bars. Looking for this specific notation, as well as being able to enter in your calculator to get your solution. And make sure that you don't put y sub 1 as your notation. It's not clear enough. Yeah, so you're going to do math 9. And then you'll go from 0 to 4. Alpha trace, call your velocity function. Get it, Ellie? Yeah. Okay. Yeah, and I'll leave all this on the board here. Find the total distance. Now this is also involving definite interval, but now we want absolute value bars around V of t. So math 9 again. 0 to 4. Absolute value, so math number ABS.
Wait, what was it? That number?
Yeah, math number ABS. Any questions with calculator entry? Next up, we're now looking for a specific location at a certain moment in time of this particle. So we know that this particle is going to end up at x value of 3 on t equals 1, but it's asking where's the particle going to end up at t equals 5. So we use our displacement formula or displacement with position formula. So make sure we know this. Any location that I'm looking for is going to involve my initial position plus displacement. So I'm looking for my particle's location at t equals 5. I have the particle's location at t equals 1. And now I'm just trying to figure out how much progress has my particle made in that time period from 1 to 5. So x of 1 is 3. So that means he's starting off at 3 on the x-axis, but then in this time interval, he's going to go backwards or go left, 0.246. So then combine that, that means that t equals 5 seconds, he's going to be at 2.7 on the x-axis. Average velocity, so this is make sure you know average value theorem. 1 over b minus a, integral from 0 to 4, v of t dt. So this enters into your calculator, divide by 4, your units of measure is back to be in terms of meters per second.
But we didn't put units on pi.
Yeah, I didn't ask for it. Yeah, so when you're on the x-axis, there's not real need for units. But if you did put units, I'll accept either way. Yeah. Any questions? Okay, next page. All right, the graph of f consists of line segments. So we know g of x is defined as the integral of f of t. And we know that means to find g, we have to involve area under the f graph. Let's find g prime. G prime, it will be the derivative of this integral. Derivative, you want to spell out what's happening here. You can put the derivative notation next to your integral, and hopefully that reminds you, okay, there's a canceling out relationship here. So derivative and integral, just basically undo each other. Just replace your variable with the upper bound. So g prime is simply f. Okay, after that, we're just making both sides go down another derivative. So g double prime would make f turn into f prime. Right, we know that anything involving with order pair for g of x has to involve area. So let's go ahead and shade in parts that we're interested in working on. You don't have to shade in, but I think it's a good way of ensuring that you're not looking in the wrong places for area. Sometimes students create areas elsewhere. So if you start by shading in, then you can just focus your attention on just that region. You're not going to look anywhere else. If you are finding areas of different subintervals, that's fine. If you're working in smaller intervals, I kind of just arbitrarily found area of these subregions. All right, g of -3. G of -3 has to involve the original definition that's provided, so let's use that. Okay. First, start by following the definition and copy exactly what the definition gives you. After that, if we see that the bounds need to be adjusted, we can adjust the bounds and flip the signs or change the signs. Go from -3 to 2. I have 1/2 here, a 1/2 there. -2, -1.
Wait, what did you do?
Okay, so this region is +1/2. This region here is -2. This region is -1, and this region is +1/2. And then 1/2 plus 1/2 is 1. 1 minus 1 cancels out. I'm left with -2. And then the -2 with the negative change in signs, which would be a +2. All right, G of 4. No need to adjust signs here. We can just add up our regions from 2 to 4. Both these squares are areas of 1, and these are half, so 1, 2, 3. Any questions so far, A or B? All right, G prime of 4. So G prime of 4, we look at the relationship that's provided here. G prime of 4 is equal to F of 4. So that should just be the order pair. By the order pair, F of 4 equals 1. All right, G double prime. G double prime is related to F prime. Just finding 3.2 on our F graph and understanding that we're just looking for the slope. So the slope of this line segment is negative 1. All right, create your G prime sign line. Understanding this is the G prime graph. So if we label accordingly, above is positive slope, below is negative slope. X-intercepts is what we want to pull from our derivative graph. Okay, see where the graph is located between -4 and -2, above the x-axis, so positive slope. Below the x-axis, negative slope. Above the x-axis, positive slope. So my G graph is rising. It's a relative max at -2, decreases. Relative min at 1 increases. So these arrows gives us the actual movement of G graph. The double prime sign line. Take off your relative max and relative mins. This is now going to give you information about concavity. So relative max at -3, relative min at 0, relative max at 3. And now look at slope. Between -4 and -3, my slope is positive. Then slope is negative and positive, then negative. And we can translate all this in terms of graph of G to be curvature information, concave up or concave down. Okay, for what value of X is G decreasing? So decreasing. G prime increasing. So G prime increasing is where G double prime is positive. Okay, find the absolute extrema between -4 and 4. So we know that is extreme value theorem, which means candidates will come from your G prime sign line. So we'll test -4, -2, 1, and 4, all back into this definition for G of X. Okay, I've followed what the definition said, but now I'm looking at it, seeing that my bounds are out of order. So then count your regions from -4 to 2. Add up those regions, and then make sure you change the sign of whatever you get. Next up, let's test -2. So add up your regions from -2 to 2. Finally, GO4. Compare all these Y values that you gathered. Highest will be your absolute max, and lowest will be your absolute min. I just provided some additional problems involving table of values and interpreting. So but yeah, your test is just 3 problems, but I just put an additional one here just for practice. Very good.
What would be the sort of difference between the first, for and chemistry?
Okay, yeah. All right, so let's talk about this here. The rate of decay in grams per minute of a radioactive substance is differential decreasing function R. Table shows the decay rate if the substance has 3,000 grams as recorded every 4 hours. So using correct units, interpret the meaning of the interval of RT. So if we're accumulating all these grams per year, the rate that the substance is decaying, then if we accumulate all these rates over that time period, we're no longer going to be in terms of grams per year. We're not going to be in terms of grams, right? Because anytime you're involving depth integral, you're thinking multiplication, you're thinking area, and that goes with units as well. You're multiplying these units together. So grams per year times year, the years cancel out. We're just talking about grams here. So this is the total number of grams of this radioactive substance that have decayed over this 12-year period. So part B is asking basically for an approximation of the amount of radioactive substance that have decayed over this 24-hour period, or sorry, 24-year period. So we're extending our intervals here. So 0 to 8, 8 to 16, 16 to 24. And then we're just doing middle rectangles. So width times height, add up your areas of three rectangles, and then your units is grams. Part C, using your answer from part B, how much of the radioactive substance is left after 24 years? So the problem says there's 3,000 grams to begin with. And so if 1920 have decayed, then we can subtract those values.
We got the, for B, we got the numbers between, what's this?
We just did we just did middle rectangles. So width times height, width times height, width times height. Okay, for B, temperature of water in the hot tub is modeled by W of T. So this tells us the temperature as it increases over this hour-long period. So 57 degrees goes all the way to 202 degrees over this 60-minute period. Okay, use the data to evaluate the depth integral from 10 to 30 of W prime. Now, this is not the W prime graph, so we don't want to do area because we don't have W prime in front of us. But what we can do is we can convert it in terms of W, because remember, first theorem says any function that you're starting off with, you can always make it the antiderivative into its antiderivative function, right? So here we don't have W prime, but we can force W prime into W of T if we go through first theorem, right? The integral of W prime will make it rise up to W of T. And this is basically just first theorem, W of 30 minus W of 10. And what does that mean? This tells us 85 minus 63, which is 22 degrees. So that tells us in this 20-minute period, the temperature is going to rise by 22 degrees.
Are we just to see one of these?
If you do, I'll give you the hint. I'll give you that integral f of x, b minus f of a hint.
Oh, you'll give us the,
Yeah, if I give you a problem like this, I'll give you that hint to help you see how you can change it into a unit that you can use.
oh, so you're gonna stack back.
If this problem is going to show up. All right, for next step, 4C. Okay, next up. A cold winter morning, hot water is poured into a large container for hot chocolate. W prime is given. So you see the rate at which water is poured into a container. 4.2 ounces per second, then 8.3 ounces. So rate keeps increasing. Okay, so the cup already holds 10 ounces of cold water before pouring in the hot water. Part A, using correct units, interpret the meaning of definite interval from 0 to 3 of W prime. Well, we know W prime is in terms of ounces per second. And then if we take the antiderivative, we're going to have to involve multiplying our units, right? We're no longer going to be in terms of ounces per second. It's going to be ounces per second times second, basically stripping away the rates because we've accumulated the rate over that time period. So if you think about this, right, if you're pouring water into a container, it doesn't matter how fast or how slow you pour into that container. In the end, you're going to have some amount of water in that container, and that amount of water, you're talking in terms of ounces, right? You're not looking at that amount of water and you're not saying, oh, this is 75 ounces per minute in my hand, right? You're going to say 75 ounces. Okay, so that indicates the amount of water poured into the container during the first 3 seconds. And then part B, we're actually going through an approximation method to actually find that value. So let Riemann sum, width times height. And then part C, how much water is in the container after 10 seconds? The problem says there's already 10 ounces to begin with. So 10 plus 75, 85. Same idea here for 4D. Integral of RFP, we're no longer going to be talking about liters per hour. We're going to be talking in terms of liters. Let Riemann sum. Okay, let me know if you have any individual questions.
Like as if you about just basically like
You have to, you're following this.
This makes sense. That's
I think it's like they call it. I don't know. But I can text them as well.
Okay. So he doesn't have first
He doesn't
period.
have
Alright.
Are you okay with using that
Yeah, I can
calculator?
use this for
Okay,
that.
okay.
I did it back like by like tonight though.
Oh, okay.
I use it for my ACT stuff.
can I text him and give him your number? Or
Yeah.
do you have, I'll,
All right, thank you so much.
I just have a question about, so like, when it says like R prime, that's when you talk about the rate.
yeah, the rate of that. Yeah.
Okay, because like here, because there's, it's not like R prime, it's just number of like rings. There's no like rate involved, right? Don't know when like the rate.
Yeah, so this is not gonna be a rate anymore because R of T is in terms of grams per year,
Okay,
and you're multiplying by time.
yeah,
So grams per
Yeah,
year,
got it.
which cancels out, which is not gonna be a gram, so no
Okay.
longer gonna be a rate.
and then even like here, there is that prime, it's still like.
No rate involved, right? Anytime, usually with intervals, there's no more, it's not gonna be a rate.
Okay, but like here, because there's no interval yet,
It's gonna be, anytime there's derivatives, it's always gonna be a rate.
okay, thank you.
I use math aids. Yeah, I did n deriv of the velocity to get. So I'm just making my calculator. find it.
Mildly. It's just Sports med, yeah. Realistically, I'll.
So you do math eight, do the dx, and you can type that in, or you can do.
On that, man. It's just, I don't know, if we were doing that, I was so confused. And it's not like horrible, but like, I don't.
I guess go back to your own space.
What do you taught that? 90, yeah, I saw, that's all I gotta get shit. He's so nice.
Yeah. Yeah, yeah.
Yeah,
It's
David's
not a-
old. Yeah, I was so.
Whatever was my. What do you not get?
So what's happening is that plot one is highlighted on the matrix. Let it go up on this side. Let's try it.
It's like.
Yeah, don't have it yet.
It's okay, bro.
Okay.
Yeah.
I think that's.
Yeah. So, it's okay if I do the. Yes, sir. I can jump. Yeah, I'll give you the first.
Yeah, that's not it.
Later. And big one time.
Oh, it's like that. Oh, stop talking to me. Hey, it's just simple. He's 35 minutes. It's time to get. What's your rate for $8?
Yeah.
Oh, is that one where it's like simulation information? Out and then read out. I said, right guy.
Yeah.
Or students. How you compare?
I have like 4 questions. They're all about this section. So I understand when you find these points, and then you can like you find it on plus or minus like other stuff or.
This is a bump. Yeah, this is slope.
Oh, whether these are.
Yeah, that's right.
Yeah.
You do math eight.
There's no way down. I'm like,
I'll get you, you're asking for the derivative of this.
oh my God.
So d over dx, alpha trace gets you.
Distance, does it have an integral? No, I can't do it.
So what's happening is that it's finding the derivative for you and then plugging into it.
Like, pull up that problem.
You're just plugging 2 directly into that function. So if you do alpha trace, you can just plug 2. Total distance, you're gonna do, on paper, you're not gonna do 1, 1, you're gonna say so you'll do math 9, 0 to 4. But now you're gonna call x a value. That number is this. Ask the value bar. Velocity function. And that will get you.
Dying with this.
Makes sense. I just remember they do things like take the distance needed out together and I did.
So decreasing, you look at your sign line, -2 to 1, negative. And then decreasing, you look at your sign line. Negative. This you look at if you prime sign line. This you look at G prime increasing, it means yeah, that's right, G prime. G prime increasing is actually about the rate of G prime. That's right. Right. This is G, but it's G prime. Now we lost.
Sine to beta, that's point 90. Because I know on the, there was some question here. I mean, no, I'm just area. Yeah, this is the area. This is just for like a vector problem.
Yeah, yeah.
Because I know there's another one where.
If I want to show me your work, then I want something that showing it be the work.
If I've gotten it, so
That's after that, you know, I just want to see that you can get there.
yeah.
Our nature plus. We always think our it's not just. Oh, no, I don't know. I don't know how to read. It's there. Good one. I know it's nice. It's great. It's 92. Well, it's not 90. The raspberry. It's like it's such like